Okay, so yesterday we did several examples on how to calculate the electric field for various configurations. We had studied the ring and we looked at the electric field along this line. Now the reason why we chose that line was twofold. One is that it is easy to calculate the electric field along that line. If you try to calculate the electric field at an arbitrary point, you will see that it's quite complicated. And the other reason was, using this knowledge, we could calculate the electric field of an infinite plane. Ring and infinite plane. And we had seen that for the case of the infinite plane, the electric field was uniform. This is the magnitude of the electric field. Now, do you have any questions on how to calculate these results? Now, the trick is, all the time, if you have such an extended object, what we do is we just divide it into very small point-like objects, or to objects whose electric field we know. Like in the example of an infinite plane, we divided it into concentric circular rings whose electric field we had already calculated. In the case of the ring, we divided into very small segments which just behaves like a point charge, so we can use the Coulomb law directly to evaluate the contribution to the electric field from each one of those segments. And then we just summed over all those segments, which in the limit that the segments become infinitesimal, so that there are infinitely many terms, in that case, the sum just becomes an integral. Now, any questions? Okay, so today let's start with a different concept, the electric field lines. I didn't mention the electric field lines up to this point. Now, when we were defining the electric field, for example, when we were discussing the electric field of a point charge, what we said was, if you remember the way we defined it, the electric field at this point, we just put a test charge over there, calculate the force acting on this test charge, divide by q prime, and take the limit as q prime goes to 0. This is the electric field at that point. So at every point, wherever you put this test charge, it will feel some force, and hence there is an electric field at every point. So if you want to show the electric field line itself, electric field, you basically need to draw a vector. The electric field is a vector. You have to draw a vector at every point in space-time, in space. But of course, to visualize that is not that much helpful. It just gets confusing after you put some vectors at several points. So this, for example, is not the electric field at all these points. It's the electric field only at this point. So if you want to show the electric field at this point, for example, that is another vector, etc. So it just becomes quite complicated. So what we do is, instead of using these, putting vectors at every point, we draw lines. Just imagine that the electric field at every point, just imagine it's the velocity of a particle. So the particle will be moving with some velocity, so that the trajectory of the particle will be parallel to these vectors at every point, but then the trajectory is just a line. So, for example, in the case of a point charge, let's say plus q, now, the electric field lines are the electric field is always pointing away from the charge. So if you just would imagine those vectors as the velocity vectors of some hypothetical particle, that object, if you just put it over here, at rest, it will just move along this line. This is the electric field line. Or if you put that hypothetical particle somewhere over there at rest, it will just move along this line. This will be the trajectory. And you can just draw as many as you like. These are what we call the electric field lines. Of course, we start them from positive charges. Now, these lines should, if you want to find the electric field itself, we have to find two information at every point: the direction of the electric field and the magnitude of the electric field. If you draw a line, at a point on the line, you already have directions. So if you just, it doesn't have to be straight. If you imagine this point, there's a tangent at that point to this line. The tangent at that point just tells us two different directions. Now, to distinguish these two differentiate between those two directions, what we do is we just draw arrows on these lines. So at this point, if I draw the tangent at that point, it has two directions, but this arrow over here shows me the direction of the electric field. So the electric field at that point is pointing in this direction. Now let me draw the electric field lines for a dipole. Hopefully it will be more clear. So the electric field of a dipole will look like this. Now we will drive why it looks like this, but this is the shape. So if you take some arbitrary point, let's say this point. So this will be the direction. If you imagine that point, we can just draw at the tangent line. This is the tangent. So a line already tells me two directions, either this way or that way. But this arrow tells me that I should go this way. So the electric field at that point is in this direction. And this way you can find the direction of the electric field at every point. So you can look at this point, for example. At that point, taking into account this direction of the electric field line, we know that the electric field at that point is pointing in this direction. At this point, it is pointing in this direction, etc. So using the electric field lines, we can determine the direction of the electric field. Now, any questions on this one? Now, one problem is, for example, if you want to find the direction of the electric field, let's say at this point. Well, first, it seems that there is no electric field line passing through that point. But remember that just like the electric field vectors, electric field lines also pass through every point. So basically what you do is you just first fix your convention. You can say that for 1 coulomb of charge, you will draw 1,000, let's say, electric field lines. Of course, that 1,000 electric field lines cannot go through any point, but in reality, you can just imagine an electric field line going through every point. There are infinitely many of them passing through at every point. So although there doesn't seem to be any electric field line at this point, there is actually one, and it should just lie between these two. So the electric field line passing through this point should look something like this. If you draw the tangent over there, this should be the direction. This is the electric field at that point. So this is how we can determine the direction of the electric field lines, the direction of the electric field from the electric field lines.
We cannot see the electric field lines, but if we approach enough, can we check these lines? What are we expecting?
No, these lines are just purely mathematical. Our invention just to help us visualize the electric field. They don't have any physical existence. So you cannot see the electric field lines. We cannot feel it. I mean, they are not things that exist. They are just we invent just to help us visualize the electric field. I mean, I cannot just put a vector at every point in space. So that won't help me in visualizing the electric field. But we will, just by looking at the electric field lines, which don't exist physically, I can determine how does the electric field look like.
Just I'm confused in this part. On this electric line, electrons are moving or something?
No, nothing is moving. Nothing is moving. It just looks like, it is similar to just imagining that the electric field is just like the velocity vector of an object. So, in fact, it is because of this property that the electric field line is always tangent to the electric field, which makes it possible to make this analogy. Nothing is moving on them. So they are basically lines that are tangent to the electric field at every point. That is the mathematical definition. Other questions?
Is that maybe this time, maybe if we put a charge in this field, this is the direction of the velocity of the...
No. You see, this direction is the direction of the electric field, which determines the direction of the force. So the acceleration of the object is along this line. So I can just throw a charged object. I mean, if I just put a charged object over here, it will of course accelerate in this direction. So its velocity vector will be pointing in this direction initially, but still it will not follow this line. Because this is not the velocity field. This is the electric field which determines the force. That is the acceleration.
So if I put a charge in the middle, it will not move to the negative part, it will move to a specific object.
No, it will just move something like this, probably. It will not follow this line. Would there be a force without the electric field? Let's look at this definition. So this definition tells me that if there is a force acting on a charge, then there is an electric field. If there is an electric field, it means there is a force acting on a charge that we put there. So if there is an electric field at that point, any charge that is placed there will feel a force. Now, another reason that we define this concept of the electric field is, you see, if you remember the Coulomb law, the force that an object feels depends on its own charge, and also the charge of the other charge. So it depends on two things. But the electric field itself only depends on the charge, the other charge. So it doesn't depend on my test charge. It's a property of how the other charges are distributed in space. Other questions? Okay, so if we want to visualize the electric field, we have to specify two things. The direction of the electric field at every point, plus the magnitude of the electric field at every point. So the tangent to the electric field lines already tells me what is the direction of the electric field. Now I have to also specify the magnitude of the electric field. And to determine the magnitude of the electric field is proportional to the density of field lines. By just knowing these properties, we can have a visual picture of how the electric field looks like by just looking at the electric field lines. So you see, let's look at this simple example. So we already know what the electric field is for this point charge. We know that it is radially outward and it decreases as 1 over r squared. Now, this same information we can also see just by looking at this diagram. Now, the lines are all pointing radially outward from the positive charge. So that tells me the tangent is radially outward. That is, the electric field is radially outward. Furthermore, if you just look at this picture, you see that the density of the electric field lines close to the charge is much larger than the density away from the charge. So we already know the magnitude of the electric field close to this point is larger than the magnitude over here. Similarly, if you just look at this dipole, we didn't calculate the electric field of a dipole at an arbitrary point. We just picked up several special points to calculate. But already by just looking at this diagram, we can determine what the direction of the electric field at some, let's say, at an arbitrary point, and we can even say how the magnitude of the electric field changes. So as you go from the positive charge to the negative charge, let's say you go along this line, it first is the magnitude is quite large close to this one, it gets smaller and smaller, and then it just starts to get larger. Or even if you go, let's say, along this line, you can tell, maybe not quantitatively, but qualitatively, how the electric field changes as you move from one point to the other point. Well, let's do some other example. Let's just imagine we have plus 2q charge over here and minus q charge over here. We don't know what the electric field is. Of course, we can just sit and calculate. But even without calculating the electric field, we can have a qualitative picture of how it should look like. Now, first of all, you have to fix a convention on how many electric field lines start or end from a point, from a unit charge. So you can say that, okay, for Q charge, you will draw 8 electric field lines. It's up to you. You can just choose just for the drawing purposes. So close to this minus charge, the electric field of this minus Q charge, it will be huge. And the electric field due to this plus 2Q charge, well, it won't be huge. So close to this minus Q, we can say that the electric field, the net electric field, is determined only by this minus Q charge. The contribution of this one will be very small compared to the contribution from this one. And if you just draw 8 lines, we know that for a point charge, at least the electric field lines are always radially out. So this is a point charge. The electric field lines in the very near vicinity should be radially out. Let's draw 8 of them. Well, in this case, since it's a negative charge, it will be radially inward. Very close to this plus Q charge, this time the contribution to the electric field of this point charge will be huge. The contribution of this one will not be huge, so it will be determined mainly by the plus 2Q charge. And it's a positive charge, so the electric field lines are always radially out. So this is 8. But we said that since we are drawing 8 electric field lines for each charge Q, here we have 2Q, so I have to draw like twice as much. I have to draw 16 of them. So these are the electric field lines very close to this plus 2Q charge. Now the next thing is connecting them. I have to connect at least 8 of the electric field lines from here. I can just connect to this one. So I know that the density here is large, so this will come here. This can go like this. This will come here. So this is basically how it will look like. The electric field lines.
That line at the axis of is it close or
Well, there will be this one going in both directions. So this will be in this direction. This will be in this direction. This will be this way. No. There won't be this one. So this is basically how the electric field lines will look like. Now, why there won't be this one? The reason is, just imagine you are very, very far away. Now, when you look at this charge distribution, you will not be able to see this distance. But if you don't see this distance, it just means that this is just a point charge with charge plus Q. So from a very far away observer, this whole system should just behave like a point charge with charge plus Q. So the electric field lines at a very far away distance should look like this. Eight of them. So let's see. There were 16 of these. 8 of them just was connected with the electric field lines leaving the minus Q charge. 8 of them were left, and that is what those 8 electric field lines will be, what the far away observer will see. So just by looking at this schematic diagram, I can already tell how the electric field lines, electric field itself will look like. So it will be dense over here, dense over here. At this point, for example, there will be regions in which the electric field line, in fact, is looking away from this minus Q charge. There will be a region over here, somewhere over here, where there won't be any electric field, because eventually this line and this line, okay, they will come close, or let's say go diverge, but there will be a point over here which electric field lines will not pass by. So I can also tell that by just looking at this figure. And you can also verify by actually solving it. A point without any charge. Well, this is a point where there is no charge. This is a point where there is no charge. No electric field. Well, let's see. Let's calculate what is that point. Here I put a charge plus 2Q. Here I put a charge minus Q. And let's say this distance is D. I will try to find a point, let's say somewhere over here, at a distance x from the minus Q charge, such that the electric field over here will be 0. So if I can solve for this x, then there is a point at which the electric field is 0. If I cannot find such an x, then there is no such point. So let's see, what is the electric field at this point? We know the superposition principle, so there are 2 charges creating an electric field at that point. The total electric field will be just the sum. So the total electric field will be the electric field of the 2Q charge plus the electric field of the minus Q charge. Note that I'm adding them. Although I know that these 2 electric field lines will be in different directions, it is vectorial sum. Now, let's just say that this is the x direction. Now, what is the electric field created by this plus 2Q charge? Just the Coulomb law, 1 over 4 pi epsilon 0, 2Q over, what is the distance? d plus x squared, this is in the x direction, plus 1 over 4 pi epsilon 0. I have the minus q charge, its distance is x. This should be 0. If there is such a point. Well, this tells me that 2 over d plus x squared minus 1 over x squared should be 0. Well, this tells me that d plus x is nothing but square root of 2 of x. If this is satisfied, if I put instead of d plus x square root of 2 of x over here, it gives me the square, gives me 2x squared, 2 cancels, so I have the solution. Well, of course, there's a plus or minus sign. There are two possible solutions. And this tells me that d is equal to, or minus 1 plus or minus square root of 2 of x, or x is equal to 1 over minus 1 plus or minus square root of 2 of x, 2 of t. Where are these points? What is square root of 2? Approximately. Well, square root of 2 is approximately 1.4. I mean, this is a nice number to remember because you will always face square root of 2, square root of 3. So x is approximately, let's say, 1 over minus 1 plus or minus 1.4 d, which gives me x is either 1 over 0.4 d or x is approximately minus 1 over 2.4. Or x is approximately, this is 2d, or x is approximately, and this is minus 0.4d. Now, one point is somewhere over here. This was our picture, plus 2q, minus q. One point is somewhere like this. The other one is somewhere over here. So is this a solution? It cannot be. So this is not a solution. Well, we did find it a solution. So what's wrong? I mean, you cannot just throw away your solutions. You have to somehow interpret it, or you have to somehow show that it's not actually a solution, although it seems to be a solution. What we had done over here is, okay, this should be 0. We said if this is 0 for these two possible solutions. But as your friend has pointed out, the electric field at this point cannot be 0. So what is the reasoning beyond using which we can throw away this solution? I mean, we know that this is not a solution. We should throw it away. But we cannot just throw away solutions. So we should also understand why did they arise and why they are not actually solutions.
If the minus 2 was positive, that was the point which is the...
Now, what do you mean by minus 2 is positive? Minus 2 is negative.
But if minus q was positive q, that will be the solution of the...
But we never put minus q is positive q. You see, the thing is, how did we write this equation?
Does the electric field lines across each other in x?
In here, you mean? at this point.
No, it's the left, the right.
So these are our electric field lines. Well, there is some, you see, there is this very slight curve over here. And this one also has such a dip, but they don't approach. Now, you see, when we wrote this equation, the one over here, in determining these directions, we had assumed that x is larger than 0. So we are looking for a solution at x larger than 0. In such a case, this should be satisfied. This equation should be satisfied. So you have to be careful about your assumptions when you are writing down equations.
When we write the equation of the negative charge, we let the x direction of the distance equals, and it's working with the the positive charge with the positive charge, somehow pointing towards the x direction, the positive x direction.
No?
And the negative charge is towards the negative x direction. Why is the x direction as opposed to the?
That's the definition of my electric field. Remember the electric field of a point charge. The E is equal to 1 over 4 pi epsilon 0 q over r squared in the r hat direction. Q being the charge of my object, r hat is the position vector at which I am evaluating the electric field relative to my charge. And r is the distance from the charge. This equation is valid whether q is positive or negative. But, you see, the electric field of this minus q charge is of course pointing in towards the left. It should point towards the left. It is pointing towards the left because this number over here is negative. I don't put an additional minus x over here. This is the result. Whatever q is, you put the q there. Whatever your r vector is, you put the r vector over there. The directions are automatically determined by this expression. In this one, it is this minus sign which makes sure that the electric field of this minus q is pointing towards the left. This is not in the plus x direction, since this number multiplying x hat is negative. I don't add minus sign just because this or that. Well, you see, at this point, remember, what is this x hat? Now that is actually this r hat over here. It is the vector, it's a unit vector pointing from the charge towards the point at which I am measuring the electric field. And here I said that both of those vectors, r hat vectors, for both of these terms is x hat. So if from the charge I draw the x, consider the x hat vector, that this is true if the observation point is on the left in the positive x direction. This is true if the observation point is on the left of minus q. Otherwise, I should put some minus x's over there. For example, if I would write the electric field plus 2q minus q. If I want to write the electric field at this point, now the electric field would be 1 over 4 pi epsilon 0, 2q divided by, let's call this distance x, again. This is my x-axis divided by x squared. This time it's the minus x plus 1 over 4 pi epsilon 0 of minus q divided by d plus x squared minus x. Again, x is larger than 0 though. X is this distance, x is always positive. Now, I have the same configuration, but this time I have the minus x hats. Basically because my observation point is on the right of both of these points.
Is it possible to find a charge or the electric field on a charge? If, let's say, x works,
It will be infinite.
it will be infinite.
Sıfır büyük eşit olamaz mı?
Well, when x is equal to 0, we have 1 over 0, which doesn't have any meaning. Okay, back to our example. Since we wrote this expression assuming that our observation point is over here and x is a distance which is larger than 0, this solution, this one, is not a solution. Since x should be larger than 0. Now it was kind of trivial to see that this point cannot have 0 electric field, but this point can. Now we know the reason why we have this solution and why we should throw it away. It actually is not a solution because we have two equations, one equation, one constraint. This is our equation, and this is a condition that should be satisfied by our solution. So there is just a single solution. Now, any questions on this one?
Other solution, does it obey to another condition?
Well, just as somebody has pointed out, or it was you, if, for example, this was a plus Q charge, then the other solution would have been the point at which we have 0 electric field. Not of this problem, though. It's not a solution of this problem.
I'm going to ask another question. How can we mathematically explain electric field? Are they like functions of hocam fonksiyon olarak?
Now, electric fields are functions. What we call in the mathematical sense, what we call a field is nothing but a function, just like any other ordinary function. An ordinary function, in fact, like fx is equal to x squared or something like that, this is a scalar field defined on the real line. Now, here the electric field is a function defined in space. Mathematically, that's what we call R cube. And its values are vectors. That is what we call an electric field. It's a one special kind of what we call a vector field because values are vectors. It's a mathematical object. I mean, this definition over here is quite, in fact, mainly mathematical. But later on we will see that it corresponds to something that actually has physical existence towards the end of the semester. Okay, other questions? Now, some properties of electric field lines. They cannot intersect. They cannot cross each other. Now, why not? Let's just imagine we have two electric field lines that cross each other. Let's just prove that the opposite of this statement doesn't have any meaning. Now, the question is, if we put some charge over here, some test charge, will it feel a force? Well, there's an electric field. What will be the direction of that force? Well, if you sum them, then there is one direction of the force. And the electric field is in that direction. So you cannot have two directions of the electric field at this point. It just doesn't make sense. The force has a unique direction, and the force divided by Q prime will also have a unique direction. So it cannot have two directions. So this cannot be, because force has a unique direction. Now what happens is, for example, if you just imagine one charge over here, plus Q, with some electric field lines, you have another charge over here with some other electric field lines. Now it just looks as if you just extend these electric field lines, they intersect. But we cannot talk about the electric field lines of each charge separately. As your friend has pointed out, for the net force, you just sum them. So you should sum the electric field lines. So if you just bring these two objects close to each other, or in their near vicinity, what happens is the electric field gets modified. It's no longer these radially outward electric field lines anymore. The electric field lines just take this shape. And they no longer intersect. This just doesn't happen if you just bring charges together. Rather than electric field lines intersecting, what you do is you just take their superposition, and once you take their superposition, you just, at the end of the day, have these non-intersecting lines. Well, there is one electric field line passing through every point. Unless E is equal to 0 at that point. So, these gaps over here, for example, that doesn't seem, we didn't draw an electric field line at this point, but that's mainly because we draw a finite number of electric field lines for practical reasons. But there is an electric field line also passing through this point. At every point, they are tangent to the electric field, so that is how we define them. They should be tangent to the electric field. Now, in fact, if you just go back to this definition, the initial property, saying that the electric field lines can intersect is just like the electric field at a given point has two directions. No, that cannot be. The electric field at a given point has a unique direction obtained by the summation of the contribution to the electric field by all the charges in the universe, in fact. And the density is proportional to the magnitude of E. They start from positive charges and end in negative charges. Well, positive charges or infinity, and end in negative charges or infinity. You cannot just start an electric field line out of empty space. They have to start from positive charges and they have to end in negative charges. This is in fact due to the fact that the electric field line is the 1/r² law. we will see in the next hour that this is actually related with this 1 over r squared behavior. Now, any questions on electric field lines? Now, to show the electric field, we will be always using electric field lines, so it's important that you understand how to interpret a picture showing the electric field lines.
How can they start from infinity? They need still a positive charge in infinity?
Well, I mean, the infinity is like a source of both positive and negative charges. Now, in actual life, let's say the Earth is neutral. If Earth is neutral, if you have some negative charge, if you hold some minus 1 coulomb charge over here, somewhere else on Earth should have plus 1 coulomb charge, or all the rest of the world should have plus 1 coulomb charge. So the electric field line starting from this 1 coulomb point charge minus 1 coulomb point charge, they will start from somewhere else on Earth. But I mean, when I look at that one, when I make measurements, I will mainly make measurements in this volume. And within that volume, the electric field line will be just straight. It will just look as if it is going to infinity. But hypothetically, let's assume that you have plus 1 coulomb charge in empty space and there is nothing in the universe. The universe has plus 1 coulomb charge as a whole. Then, of course, the electric field lines will not end anywhere. Now, don't take infinity as really infinity. Most of the time, what we mean by infinity is sufficiently far, far away, in a far, far away galaxy, for example. Okay, see you after the break.